All right, today we are cracking the code on the secret engine that powers, well, pretty much our entire digital world. I'm talking secure messages, online banking, you name it. And what's wild is that it's a type of math you actually use every single day, probably without even realizing it. And it all starts with something you've seen a million times: a clock.
So here's the central puzzle that all of cryptography is trying to solve. How do you create a mathematical process that's super easy to do in one direction, but just about impossible to undo? Think about mixing two colors of paint. It's easy to stir them together, right? But try unmixing them. Good luck. We need to build a one-way street for numbers.
And this really gets at the heart of it. The math we all learned in school, that's a two-way street. If I give you an equation like y equals 2x plus 3, and I tell you the answer y, you can always work your way back to figure out x. It's predictable. But for secrets, for encryption, we need the exact opposite. We need a trapdoor, a mathematical function where you can fall through one way, but there's no way to climb back out.
So where do we find this magical one-way math? Well, funny enough, the answer has been staring us right in the face the entire time. Literally. We find it on a clock.
Okay, let's try a quick thought experiment. If I said, hey, let's meet at 14 o'clock, you wouldn't be confused, right? You'd instantly know exactly what time I meant. So what time is 14 o'clock?
Exactly. It's 2 o'clock. See? You just did it. Without even breaking a sweat, you just performed the fundamental operation of cryptographic math. You instinctively took a number line and just wrapped it around a circle. And what you just did has a formal name. It's called modular arithmetic. It sounds complicated, but it's not. All it means is that we're dividing by a certain number, in our case 12 for the clock, and we only care about the remainder. So 14 divided by 12 is 1, with a remainder of 2. That's our answer. We'd say 14 mod 12 is 2. That number 12, the size of our clock, that's what we call the modulus.
So why is this wrapping around so incredibly important? Well, because in the world of encryption, infinity is actually a huge problem. We can't have numbers just getting bigger and bigger forever. We need a closed, predictable, finite universe for our numbers to live in.
And this shows the difference perfectly. Standard math, that's an infinite number line going on forever in both directions. But modular arithmetic, that operates in what mathematicians call a finite field. It's a closed loop. It doesn't matter how huge of a number you start with, when you're done, the answer is always going to be one of the numbers on that clock face. In our case, somewhere between 0 and 11.
Okay, now this is where modular arithmetic reveals its true superpower. It is the ultimate pattern scrambler. It takes beautiful, predictable order and completely transforms it into what looks like pure, absolute chaos.
Think about it like this. If you graph a simple equation like y equals x squared in regular algebra, you get this beautiful, elegant, symmetrical curve. A parabola. It's clean, it's totally predictable. You know one point, you can pretty much guess where the next point is going to be.
But now, watch what happens when we add just one tiny little thing, that mod n. The graph of y equals x squared times mod n doesn't just bend the curve, it completely shatters it. That beautiful parabola explodes into a cloud of dots that looks like static on an old TV. The predictability is completely, utterly gone. A tiny change to the input can cause the output to jump to a totally different, seemingly random spot. There is no simple path for an attacker to follow.
And that pattern scrambling, that chaos, that's what creates the hiding place for our information. Because we've destroyed the predictable path back to where we started, we finally created our perfect one-way street. And this really gets to the core idea here. We call this information loss. And look, in normal math, losing information is a disaster, right? It's a mistake. But in cryptography, it's the entire point. It's the goal. The final answer is deliberately designed so that it doesn't have enough clues left to figure out the unique number that created it. This little funnel is the perfect way to picture it. We can take all these wildly different numbers, 2, 14, 26, 38, you could go on forever, and we pour them all through that mod 12 operation. And what comes out the other end? They all lead to the exact same answer, 2. We've collapsed a whole bunch of possibilities into one single result, which means we've hidden which number we actually started with. Which brings us right to our final and most important question. If I do my secret calculation, I do my mod 12, and I tell you the final answer is 2, which number did I start with?
Was it 2? Was it 14? 26? Or was it some astronomically huge number you could never guess? The truth is, you have absolutely no way of knowing. And that ambiguity, that irreversible loss of information, that is the mathematical lock that keeps our entire digital world secure.